Okay, so when we're talking about the globe, we split it up into different segments, so we can pinpoint any location, absolutely any location at all on the world. So, for example, if we want to know, where Australia is or something like that, we need to use some coordinates to help us get there. So the globe is obviously a 3D space. We treat the globe as a perfect sphere. Now, it's not in real life. I mean, technically our world, when I'm talking about the globe, I'm talking about planet Earth, the place we live. I mean, realistically, the planet is actually a bit more flat like that. I mean, that's exaggerated because of gravitational force. It's a bit flatter on the top and on the bottom, and also because of the pull of the sun too. But let's just ignore that for the, and let's ignore that for the reason. So you're going to treat Earth as a perfect sphere, okay? And with it, what you're going to do is we actually treat everywhere as a radius. If you stand right in the middle, which you can't stand, if you're right in the middle of the Earth, they buried you at the center of the Earth, and you went out every point from there outwards, we treat that in further mass as 6,400 kilometers. So that's a really important number to know when you're doing your calculations. You'll notice it's 6,400. Now, I can apply this same thing with a tennis ball, all these theories. So sometimes they do throw you different questions of a sphere in, but typically it will be a globe. So, for example, Australia down under is like down here. So how do I say what that coordinate is on the surface of the planet? Well, what they decided to do was a couple of things. First of all, they decided to have lines that go around the globe, and we split it this way. So we're going to split, everything will go through the North and South Pole on these ones. So they will go right, around the globe, basically, and they will split those up. So then, wherever it falls on here, like if that's Australia, it falls that one. However, I mean, a lot of places would fall on this line. So another line they use is this one. And then what they do with this is they, break this up as well. Now, so this line would be here, and this line would be here. So you can see how, we can see where, where we're at. We would be, I missed that line, let's just say we're here. We would be on this line and this line, and that's how we give the coordinates of that. So let's think about how we break it up. So what we have is we have a couple of lines with these. So the first one is our longitudinal lines, okay, which are these ones. So all the longitudinal lines go through the North Pole and South Pole. So it's almost like if you had an orange and you're cutting straight through it. Okay, you could spin the orange around and you could cut through any section and it would still give you a perfect half. How do we determine where the points are? Like if they're all going through here, if everyone perfectly goes through, it's going to cut the Earth perfectly in half, but you're cutting through a different section. How do we determine, where each of these points are? So what we did is it really came down to a bit of history, and it came down to the first people who, created a map. There was a lot of maps floating around the world back in the day, but England was one of the main places that really mapped a lot. They went out and sailed ships. So what they decided to do is, if you actually look at the world map, look at the world globe, and you go to a place called, if you go to Google Earth, let's have a quick look at this one, and there's a place called Greenwich, and it's a pretty fascinating place. That is actually where they decided in Greenwich which is kind of located up in the Northern Hemisphere, but that is where they did all their geometry measurements from. So it has a bit of history, which you can look into. And come on, Google Earth, why hasn't it started? This went a lot quicker for me before. So if you look for Greenwich, you will notice, which is right here, there's a place in here. And this place in Greenwich is actually, in London. And from here, there's actually where they did all their measurements from. It was like the meridian. But basically, if you look at the coordinates of that, you will notice that it should be anyway. If we look at that, it is pretty much on 0, 0. Like, so if I go. If you look down the bottom right-hand corner, just down here, I'm just going to move my mouse. I think this is the observatory. This is where they do all their measurements from in this building over here, where it was historically done. That there is exactly at 0, 0, 0 degrees east and west. It's at 51 degrees north. So what they decided to do is we have to give some place in the world a location. So this place in Greenwich, if it's right on the front, they called that 0 degrees. So they said, hey, this point in the Earth is going to be 0 degrees. From here, if you're standing in the middle of the Earth, so we've got the Earth, you're standing, like you're not standing, let's just picture you're in the middle of the Earth. From there, if you move this way to Greenwich, or you're moving, this is north, this is south, this is east, right? You move east. So you'll be right in the middle of the Earth there, I should say, not this one. Please ignore this one. You're standing right in the middle here. So that is Greenwich there. Let me just draw a better circle for you guys. I'm just going to raise this one. I don't like that, because I can make it a lot clearer for you. I've improved my explanation of this since it came in. This is a new study design since 2016. We never used to study it. So if you're standing right in the middle here, okay, and this is 0 degrees, right? So you're going 0 degrees is going around the globe. Okay, so that's going on the outside of the globe, and that's 0 degrees. So if you are looking at the middle and just say you're coming straight out here, that's 0 degrees. If you start looking this way and say that angle in here, so I'm talking about if I take a cross section of the center of the Earth, you're in the middle, this is 0 degrees. So Greenwich falls on this meridian line on the outside. So Greenwich is up here. And if you move, say, that angle across, and that's 30 degrees, you've moved 30 degrees to the east. So the coordinate of that line there, there we go, that's the line I want. That is 30 degrees to the east. So we can call this 30 east. So that's how we move left and right. Now, if I move to the west of this line, so let's just say it's this line over here, and let's just say that makes 40 degrees from here. That is, and that would form this line, right? That line there is 40 degrees to the west. So that's how we do it. Now, London isn't here. Now, this, what we're talking about, on the equator, is 0 degrees north and south. So before we move off latitude lines, the maximum latitude you can get is right around the back. So right around the back, you could say it's 180 degrees. You could say it's 180 degrees east, or you could say it's 180 degrees west. So you don't go any further than 180, because then you can get all the way around the globe. So you can get anywhere from the globe if you stand in the middle. Basically, if this is north that you're looking at, if we just take this cross section out, right? So that's 0. So you can get anywhere to the west around to 180, or anywhere around to the east 180. So that will get you anywhere around the globe, left or right, or east or west, as we say. So that's one of them. So they're basically called longitudinal lines. Why do we call them longitudinal? Because they're quite long. They're all long lines, and they go the lengthway around the planet. But we try and call them those because they go vertically up and down, but they're all the same length. The other one we've got is latitudinal lines. Now, latitudinal lines are slightly different. Latitude splits the Earth, and that's measuring about how far up north or down south we go. So if you think about those, the latitudinal line, because Greenwich is actually, when we looked it up here, so if we look at that, if we're standing in the middle of the Earth, and just say Greenwich is there, so that would be 0, right, degrees. So this way would be west, that way would be east. I've sort of rotated the Earth a bit. That would be 0 degrees, east or west. But if you look at going up, because this point here would be 0 degrees east and 0 degrees north or south, but you've actually gone up about 57 degrees. So when we're talking about latitudinal lines, that's going to fall on here, right? That's going to be, you know, this cross section of the world there. We're talking about from inside the middle of this ball, how far up north you've gone or south. Now, clearly, if you think about north or south, the highest angle you could go would be 90, because you wouldn't go like 110, because 110 you would just, you know, 110 you'd actually go 70 degrees up and then rotate around on the west or the east to hit that point. So your latitudinal lines only go from 0 to 90 degrees, and they can give you a measurement either north or south. So north, meaning I'm looking up in the northern hemisphere, how far north and how many degrees I've gone up from the equator, because 0 would be straight at the equator. So if you said 10 degrees north here, so if I had a line here that fell on this point here, if that was 10 degrees in there, that would be a coordinate. This coordinate here would be 10 degrees north, 30 degrees east, because I've gone 30 degrees east from the 0 line, and then I've gone 10 degrees up from my equator, north. Now, if I went down here and it was 10 degrees down from underneath, that would be 10 degrees south, 30 degrees east. And that's how the coordinates work. So the latitudinal, 0 to 90, north or south, and longitudinal lines, I'm just writing really shorthand, gives you from 0 to 180, you can't go any more than that, east or west. Whoops. And that's how we can get to any position on the globe. So going back to what Australia is, like if you look at Melbourne, if we look at Melbourne, for example, so that's the 0 line. So if I zoom out of Greenwich, so we keep on going. Sure, there's a quick way you can do this. So, you know, we're talking about the whole world, right? So you're talking about, oh, there's Greenwich. Now that, all the coordinates along here are 0. If you look at this north, I think I should be right. See, it's pretty close to 0 there. So, you know, they're all, where are we? 10 degrees east. Maybe it's a bit rotated. Yeah, it's about there. So you can see that, you know, all these ones, I think the Earth is slightly rotated. I think I slightly rotated. Is 0 degrees would be along here, right? So that's, you know, the 0 degree line, basically. So as we move across from here, if you just watch down the bottom right-hand corner and just watch this east-west coordinate, because that's the north coordinate. So as we move across, you can see it's getting more westerly. That one is, it shouldn't be. It should be getting more easterly. Am I going the wrong way? Where have I orientated? Oh, it's because I haven't orientated the globe correctly. That's why. I've got to orientate it with Australia. I don't know my continents. I've got to find Australia first. There it is. Right, there's Australia. I've got to rotate this globe somehow. There we go. Okay, so the world map is kind of like that. There we go. That's better. Aha, I feel much more better now. All right. So there's Greenwich, right, on the 0 coordinate. So as we go through here, that's pretty good effort. I've sort of orientated the globe correctly now. That's 0 degrees, as you can see. As we move across, if you look down the bottom here, notice it goes more easterly. So we move more easterly. And notice your northerly doesn't really change. So let's try and find the equator. So the 0 point in the world, which is really interesting, is in the middle of the ocean, which is kind of sad, I think. But anyway, it's kind of around. There. So that's 0, right? So 0 goes through all here, you know, north, and then you go south. So notice as I move up, we get northerly coordinates from here. So we're going to get northerly coordinates. The more north we go up, because we're measuring it from the center of the Earth, how much of an angle we've gone up. come down to the equator, we get to 0. And then when we go down below the equator, it starts moving south because you get to every point. Now, as we move to the right, it's going to get more easterly. As we move to the west, it's going to get more westerly from those points. And that's how the points work. So Australia is, we're actually not a full 180, but there's actually a date timeline, but we're pretty far around to the east, okay? And then that's what we call the international date line, starts from here. So the new day starts from there, so that's why we get New Year's Eve before everyone else. But if you look at Melbourne, like Melbourne's roughly around here, so we're talking about we're 143 degrees east, and we're 36 degrees south. Okay, so if we look at that, so it's about 145 and 36. So, you know, we're talking about, if we're looking at this diagram that we go back to, if that's 30, this is 0, we're right around, you know, because that would be 90, and then you're down the south. So it would be on the other side of the globe, sort of down here, you know what I mean? So you'd have to turn around about 100 something and then go down 36 degrees and you'd be around there. So that's how that one works. Can you guys just give me a bit of feedback between 0 to 5 about how you think, you know, these meridian lines work? So we call them, you know, longitudinal and latitudinal lines. Like 5, pretty clear. 0, I've got no idea what you're talking about. 3, I think I understand. 4, pretty well good. That'd be great for me to know if I should move on or not, or I need to go to something else. Greenwich. Thanks for your feedback. Such an amazing place, the Earth. Where's 90 south? Oh, it's a hard one to find. Cool. Okay. So really, again, there are some more videos that you guys can have a look at, but latitudinal lines give us the direction how far up or down we've gone. At 0 is around the equator. And longitudinal lines give us the direction of how far east or west. So if you're sitting right in the middle, if you use latitudinal lines, it's about how far across we go. So it goes around to 180 easterly, 180 westerly. Latitudinal lines give us an idea about how far north or south we are. So then you'll be coming up here. Okay, let's look at how this works with some questions on this. Yeah, so that's it. So how do we figure out the distances between points? That's where we're really going. So when we're looking at distances between points, that's where we're going to be looking, you know, at these ones. You're looking at a couple of things. So you could have a globe. You're going to only get in further mass 2 things. Either the points are going to be on the same longitudinal line. So that's center of the globe. So they're on the same longitudinal line, and you've got to find the distance between these two. Or the points are going to be on the same latitudinal line. Should have drawn my line first. You get what I mean, on the same latitudinal line. Depending on what happens, depends on how we solve it. This is easier. This is a bit harder. As you can see here though, this would make a big circle, where this circle would be a lot smaller, like, because all you're really actually trying to do, if you want to find the distance between those, is find out a sector and just the perimeter of that sector of a circle. Here, you just measure it from the middle, and you're just going to find out the sector of that circle, just the perimeter of that, right? So this is what we call the greater circle. And why we call it greater is because it's a big circle, and this one we call a smaller circle. Now, the only time when you'll do a greater circle of 2 where they're on the same latitude would be when it's on the equator, because the radius of this would still be 6,400. The radius of this is 6,400. The radius of that is 6,400. So note that one would actually be a greater circle. This one here, when 0 degrees north. Okay, so we're going to look at this one first and how we solve that. So, for example, if you're given 2 points, and let's just say you want to find the difference between, you've got a coordinate, 30 degrees north, 60 degrees east, and you want to go 50 degrees north, 60 degrees east. What is the distance? Between these 2 points? Between the surface of these 2 points? On the surface. Now, why I'm saying the surface, I'll tell you why. Because otherwise you'd be going a direct line, but we want to like travel around the world, right? So if you think about where those points are, well, let's think of this is the center of the Earth. This is my equator, right? So that's the center of the Earth where I did that point. This is the equator. Now, 30 degrees, if this was 0 degrees east or west, 60 degrees east or west would probably be around here. 30 degrees north, probably about there. So if you now go 30 degrees north, 50 degrees north would be about here. So we've got our 2 points. So you would notice that that would actually that would go all the way around the world. Now that 60 degrees east would also then be with 120 degree west. You know, that if you took it, that would, this line that I'm drawing now would be 120 degrees west. So that easterly only goes on one side. Okay, that's 120 degrees west, the back end. But I've just drawn the circle so you can see what we're doing. If I cut that out, just this one, and I'm going to redraw that for you guys just to show you what we're doing. So I'm going to cut out, you know, that latitudinal line there, just because then we can sort of see what we're doing a bit more. And I'm facing it straight up. If I cut it out, it's going to make a circle. So just think of it as an orange. You cut it out. Here's the center of the Earth. We had 30 degrees north here and 50 degrees north there. Now, we know that's gone up 30 degrees from here. And this one's gone up 50 degrees. And yeah, it's probably not really to scale. I understand that. That's probably more like, yeah, it's way off. But anyway, so that's 30. This one here, I should have done this bigger, is 50. If you want to find out the distance from here to here, well, the angle of this, and we know that this is 6,400. So really, all I want to do is I want to figure out that distance. The degrees in here is going to actually be 20 degrees, right? And this is 6,400. Now it's just a sector of a circle, right? And we just want to find the perimeter. Well, the perimeter is 2 pi r, except we've only got 20 degrees of 360. So you do your degrees, I should do, of 360 times 2 pi r. So hopefully that becomes pretty easy. So now it's just going to literally be 20 degrees of 360 times by 2 times by pi, and the radius is 6,400. And that's it. So when they're the same northerly, you're going to take the difference between them. Now, let's just say we throw another point in there, though. Let's go 50 degrees south. So let's look at 30 degrees north, 60 degrees east, and the distance between 50 degrees south, 60 degrees east. So this is on the same longitudinal line. Now that would look a bit different. So I take a cutout again of that. I'm standing at the middle. That would now be 30 degrees north, but 50 degrees south. Oh, that's a terrible 50. So you would add these because that's going to be 30 here and that's going to be 50 here. Okay, so that's 80 degrees in total. So again, you just want to find the distance between these 2 points. It's just the arc of a circle. So what you guys will find is when you've got these that are both the same, if these are different, you add them. If they're the same, you subtract them. And you're always going to use the greater circle because it's always going to make a big circle, because it doesn't matter where you are, the radius of this is always going to be 6,400. So this is going to be 80 degrees over 360. And I'm not doing the calculations because I know you can do the calculations. I'm just trying to get you to understand the math of it. So that's the formula for a greater circle. You guys can give me a bit of feedback on that, 0 to 5, about how well you feel about that. And then I can move on. Yeah. How are we feeling? Pretty good, I hope. So the other one is another longitudinal line. Now there is another longitudinal line which falls on the equator. So what we can do here is, if you've got a point here and a point here, and let's just say that is, we've got 0 degrees north and it's 30 degrees east. And let's say we've got 0 degrees north and let's go with 40 degrees west. That means, you know, if this is my 0 here, degrees east, this would be 30 degrees east, and this would be 40 degrees west. Now I'm going to cut it in half along there and then flip it open. So what that would look like in terms of a circle, if you think about it, would be like this. So that's our 0 line. The diameter of this would still be 6,400. We know that that's 30 degrees, and we know that this over here is going to be 40 degrees. So again, if we want to find the distance between these 2 points, that's going to then be 70 degrees over 360 times by 2 pi times by the radius, and the radius here is 6,400. Now, obviously, because this is on 0, it's a greater circle. That's the only time. But if they're different east and west, you're going to add them. However, let's just say if I had something 50 degrees, right? If we had 50 degrees, clearly then we're going to take the difference between those. So if we had another one, so if we went 0 degrees north, 30 degrees east, and we want to find the distance between 0 degrees north, 50 degrees east, the circle will be a bit different. So, you know, you're on your, that would be 0. So that would be 30. This would be, that would be 50. The total thing would be 50. So the difference between these would be 20, right? So really what you're trying to find out is the distance between these, and that is 20 degrees. Okay, and that's 6,400. So that would be 20 over 360 times 2 times pi times the radius, which is 6,400. How do we feel about those? I hope you guys are feeling good. If you can give me a bit of feedback on that, that is your greater circles. We're going to look at smaller circles next. All done. Great. We're going to look at the smaller circle, which is slightly different. Now, there is a pretty easy thing. You can use sine or you can use cos, but basically you do cos of how much of the angle you've gone up. But I'm going to explain to you why that works. So a smaller circle is slightly different, and where the smaller circle occurs is, well, let's look at our example that we had before, right? This time, you're still in the middle of the circle, but you've got 2 points. You've got a point here and you've got another point here. Now, they're going to fall, right, on a smaller circle. Because if you want to find the distance between these 2 points, you really need that circle there. And that circle there, if I take this circle out, is going to be, let's just say that this is, I'm trying to remember how far north we went in the original question. We're going 50 degrees north. Let's go 50. So let's just say that's 50 degrees north. So you've gone up. So we've got 2 points. This point here is 50 degrees north, 30 degrees east. And this one here is 50 degrees north. And let's go with 40 degrees west. So if I take a cross section of that, I mean, you could easily figure out the distance of that, right? So that would be 0 degree there. This would be 40 degrees to the west. And this would be 30 degrees to the east. And yes, it's probably way out of proportion. Let's just give 0 over here. So totally that's 70 degrees, right? But the radius of this, we don't know, because it's not the same radius as around here, which is 6,400. So we need to find out what that radius is. And how we find that out is not too difficult. So I'm going to draw another globe just to show you how we find that out. Here's my globe. That's a really bad globe. That's my middle point. Now, if I went straight out to this point, and that point there is 50 degrees north, 30 degrees east. From here to here, that would be 6,400, right? I mean, it would be. Oh, then what I can do is I also know, though, like it's gone up 50 degrees north, right? So what I'm trying to find out is you know, what the width is of this circle. Now, I know that if I went straight from here up, that would go all the way. That would also be 6,400. But what hopefully you can see is that I can actually make a right angle triangle here. Okay, so that line goes all the way up. So that's 6,400. So what I can do here is that line here is 6,400. Right? I know that I'm trying to find this distance here and here, right? Now I want to know this length, don't I? Now, how far north have I gone? Well, I've gone up 50 degrees here, right? You with me? So hopefully you can see that, you know, we've gone up north from way out here. You know, we've gone up 50 degrees. So we know that that's 50 degrees. That's where I'm getting my 50 degrees from. But we want to know what this length here is. Because if you think about it, that goes straight up. That would make a right angle, right? With this point here, like the right angle's there, you know, it stops there. So I've got a little bit of information. So we've got this. Now, if you think about corresponding angles, and this is the beauty of this, I know that this is obviously going to be 40 degrees. This is going to be 50, right? Because it's corresponding to your 50 degree north. And we know that this is 6,400. I want to know this length here to get the radius. Like, because if we get that radius, we're set, right? Because all we need to, because we know that this question so far is going to be 70 over 360 times by 2 times by pi times by r. And we don't know what the radius is. The radius is x. So if you think about this, we've gone up 50 degrees north. So how do we find that? Well, if this makes a right angle triangle, can't we do SOHCAHTOA? This is my adjacent over my hypotenuse, which is cos. So what you do is you actually, to find the small circle, is you can actually multiply that then by cos because that's going to be, so if we want to figure that out, I'll just show you guys on this one first before I go to that, sorry. So this is cos. So this is cos 50 equals cut adjacent x on hypotenuse, 6,400. Now rearrange that. That's going to be x equals 6,000. That's going to be x equals 6,400 multiplied by cos 50. I'm running out of room. I'll just move it across. 6,400 multiplied by cos 50. So the rule here, what you can write it as is by cos 50 by 6,400. So what you'll find in Enrollo, what they do is they give you this formula. The angle between your 2 points over 360 by 2 by pi, and this is only for smaller circle, guys. I mean, you can use it for everything. By cos, this angle here would be actually, I'm not going to write that. They call this one the angle of, what do they call that? I'm trying to recall. Angle of elevation or depression for the small circle. So I do like the way they do it here. So I'm going to write north or south for you guys. Oh, and whoops, I'm going to do by 650. So I'm going to write this 6,400 by cos north or south. And that will get you out of any trouble. Alternatively, that's one formula. So this is one that I would definitely write down in your reference book. I will come back to that, but just stick with me. Hopefully that makes sense. There is another one that you could do though, and because I have seen it pop up occasionally. I mean, if this is 50, right, couldn't you use this to figure it out? Now, if I wanted to figure out using the 40 degree, that would be my opposite over hypotenuse. So that would be, sine 40 equals opposite x over 6,400. So x would be equal to 6,400 times sine 40. Now, if you think about how you get this sine 40, it's really how far north, it's 90 minus how far north you've gone, because that's going to be the other angle, right? Like north, because that's 90 degrees minus how much you have in there. So another formula you can have, because they may give it to, like they might have a multiple choice that says it with sine, would be the angle over 360 times by 2 times by pi times by 6,400, and this will give you the distance between 2 points, times by sine 90 degrees minus north or south, how far you've gone north or south. And that would be the other one. So there are two formulas that you can use, and that will tell you the distance between 2 points. So, for example, we had these 2 points over here. How can we do that? I'll just zoom out a little bit. So we had one at, where are we? These 2 points over here. So we got 50 degrees north and south. So I've noticed that, it's a smaller circle question because it's both on the same high north. So for that, if I want to find out the distance between those, 40 degrees west and 70 degrees east, well, the difference between those is 70 degrees. So it's 70 over 360 times by 2 times by pi times by 6,400. And I've gone up 50 degrees by cos 50 degrees. Or I could have done sine 90 minus 50, which would be 40. And that would give me my distance. Now, just take note, if we had another point over here, and if that was actually 50 degrees north and 50 degrees east, and I wanted to find the difference between this point and this point, these 2 points, I would need to subtract 50 from 30 because they're both easterly, because only 20 degrees difference. So the only difference there is instead of 70, it would be 20 over 360 times 2 times pi times 640 times cos 50. And that one is it there. And that's the smaller circle. Even if you've gone south, if it was like 30 degrees south, if they're both on 30 degrees south, that would change to 30. And hopefully that makes sense. Why? Because of this. So that is this subchapter. That will get you through all of it, understanding them, figuring out where they are. Again, if you're on the equator, you can just use a small circle. But I mean, you could still put in literally, you know, cos, because it's about how far. If you put in cos 0, that's just going to give you 1. So, you know, even if it's on the equator, it will still work. It doesn't matter. So that's only when they're different in that manner. So that is the two there. So hopefully you should be right. So that is L and then L and N for you guys. Pretty much those ones. So that is meridians. Looking at those, looking at the points on those. And if we look at N, L, that was N, wasn't L? Actually, okay, L. Sorry. Pythagoras' theorem and spheres is pretty much a very similar concept with what we just did there. So just finding out, just doing it exactly the same thing with distances between them. So N, just going through this one, is using Pythagoras' theorem to solve 2- and 3-dimensional problems. Between those, really pretty just using right angles and just finding those. So for example, a scoop of cookies and ice cream, and cream, ice, whatever. A scoop of cookies and cream ice cream is placed in a cone at Ben & Jerry's. The cone is 10 centimeters tall and has an external surface area of 222 centimeters. Determine the diameter of the ice cream scoop correct to 2 decimal places, given the radius of the cone and the radius of the ice cream scoop are the same. So we have the cone is 10 centimeters tall and has an external surface area of that. So you would need to then figure out what the radius is from the cone. So you basically put in the area and you can figure out what the radius is. Once you figure out what the radius is, we need to go back to figure out the radius of the ice cream scoop equal. So then you'll get to that answer there. Have a work through these ones. You will probably find this will be a bit more of prior knowledge for you. I think you will be fine on this. I'm going to leave it there for you and have a go. If you got any questions, please yell out. A lot of the time, if you work through that, Pythagoras' theorem we've done, where it really comes into play was what I was doing with the smaller circle before. So you should be fine with that. So for example, 2 locations A and B are lying on the same latitudinal N. Okay, so they're both northerly. Longitudinal A is 50 degrees west and B is 30 degrees west. Find the distance between around the 40 degree latitudinal. So again, there is just the small circle. So there's 20 degrees between them. They're both on 40N. So your answer for that one, you'll just be using your compass here. That would be, what did we say it was between them? 20. So it'll be 20 on 360 times 2 times pi times 640 times cos 40. So that's the similar concept that I tried to approach to you guys, talking about how it's just going out here. We know that's 6,400. We want to know the radius, therefore that's 40 degrees. So we've covered that one. Hopefully that will help you with that one there.